Hello everyone, welcome to this tutorial. My name is Amir Senahri. I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to calculate color dissolved organic matter using Sentinel-2 imagery in the Google Earth Engine platform and Python API programming. This tutorial is useful for those of you who are interested to know more about the water quality and Sentinel-2 image processing. At the end of this tutorial, you will be able to produce a multi-temporal map for the dissolved organic matter using Sentinel-2 imagery for the coastal area. So now I'm gonna show you how to do this calculation from scratch in the Earth Engine platform. In the first step, you need to make a notebook in the Colab environment. So in the Colab environment, first we need call essential libraries we want to deal with. So as I need to make a connection between Colab and Earth Engine platform, it's essential to start with EE library. So import EE library first. The EE help us to make a connection or establish a connection between Earth Engine and Colab environment. So now I'm waiting Colab connected to the server, and then we can have it as a library or package in this environment. The programming is based on a Python in this area, and it is really easy to do, and there is no problem for all of the earth science users because everything simplified so you can do your programming task without any challenge. And I will try to show you how to do this procedure from the scratch. So now Colab connected to the server and library imported. Then the EE help us to do the authentication and initialize the Earth Engine account, just like that. Two arguments necessary here. First is the project ID. If you want to find your project ID, you need to go to the code.earthengine.google.com. In the code editor environment, you can find your project information. So as you can see, here it is my editor, and upper right there is my account information in the Earth Engine. Go to the project info and then you can find yours cloud project ID. So now I'm adding my project ID. Every user has a specific project ID for own self. So the next argument opt URL. So the URL address is available in the XEE library webpage. If you search about the XEE library on the net, you will find a detailed instruction about XEE library under this GitHub address. So if you scroll down a bit in this page, you can find the OPT address. So let's copy, paste into the code. Now run the authentication process. There is a pop-up then asking you permission to get access to your Earth Engine account. Now the permission granted by the user after clicking on your account information. Then continue and continue. Now we are waiting for the connection. So from now on, we have access to the Earth Engine capabilities, functions, data catalog, and everything under Python standard. So in the next step, I need to bring a user interface to select the study area before further processing. To do this, I need to import GEE map library. So you can see GEE map inserted by the import. These are built-in libraries and you can add them by a simple import. So make a new variable map. From GEE map library, I want to call the map with a satellite base map. Let's run. After a few moments, you will have a user interface like this, where you can identify your region of interest without any challenge. So a little zoom in, and you can find a water body or a coastal area wherever you want. This tutorial is not limited to one single or specific location. You can use this tutorial for all around the world. Just it is important to select the water body. I prefer to select a part of the Persian Gulf in the south of the Iran. So the coastal area in the Persian Gulf detected here. So now I'm gonna select this part of this area by the rectangle or the drawing tools available, just like that. So then we need to have a rectangle as a variable in the code. So ROI, the region of interest, sets to from the map, select the last feature. Select the last feature, convert it as a geometry. Let's run the ROI. So as you can see, the study area selected as a polygon and also callable inside the code as a variable. That's important because we need to bound our dataset based on the ROI. So now we need to call the Sentinel-2 images in the Google Earth Engine platform. Now, if you search about the Sentinel-2 and Google Earth Engine data catalog, you will find this page, Harmonized Sentinel-2 Multispectral Instrument. The surface reflectance product, or level 2A, is a kind of product already corrected atmospherically and radiometrically, and no longer atmospheric correction needed. So that's our main option for the spectral indices calculations. The Earth Engine image snippet available here allows you to collect the satellite data. The satellite variable is Sentinel-2. Make a tuple and paste the image ID just like that. So now I can call Sentinel-2 using image snippets. However, I need to have the probability band also for every Sentinel-2 image in the corresponding dates. So now if you search about here, you can see Sentinel-2 cloud probability that's available in the Earth Engine web page. By a simple search on the net, you can find its page or you can see its address. If you search about Sentinel-2 cloud probability on the Google, you will find it without any challenge. So, and also the datasets link also attached below this video in the description box. If you failed or if you couldn't find the web page address, you can find them below this video. So now let's copy and paste. Here we want to actually join two image collections. The first Sentinel-2, the next cloud probability image collection. So the link collection, there you go. The link collection is a function allows us to do this procedure. So the band name here mentioned the probability. After the image snippet, the band name probability added, just like this. Then we need to define the filter bounds and filter date as it is already suggested by the AI tools. So that filter date, I'm gonna calculate the monthly dissolved organic matter for 2024, the most recent images, 2024 to 5. That filter bound, I need to find those Sentinel images for the selected area as a ROI. Let's run the Sentinel-2 to see what do we have right now. Code is running. So now everything is doing in the Earth Engine platform right now, but only we are using the Python script for working with Earth Engine platform. So the processing is actually undergoing and I'm waiting to see the results. If you face with any challenge in this tutorial, feel free to find the feel free to find actually the code example below this video in the description box. So as you can see here, we have over 500 elements for the selected year and study area. For every date, there are 27 elements, but not all of them refers as a multispectral dataset. The multispectral bands highlighted with B1 to B12. Here we have 13 multispectral bands available here. The rest of the bands are complementary information for the pre-processing and the further analysis that is not useful for this tutorial. As you can see, the probability band is also added to the end of each dataset from another collection. So now I have a one probability band and couple of multispectral bands. Combination of these two sets of data helping me to actually calculate the clot-free color dissolved organic matter without any challenge. Now I'm gonna show you how to do this. Make a function by the def. A function starts with def in a Python, and the function name, for example, is index. We have one input for the function that is the image for each date. In each image, we have a property band, probability band, so that we call it clot band. From img, select the probability, just like that, probability. And now I'm gonna find the clear pixels in the clot band. From clot band, select pixels there where the clot probability is less than 20%. I consider pixels with less than 20% probability as a clear pixels. The rest of the pixels above this threshold will be removed. So, in the next step, I need to find or select the multispectral bands, all the bands starting with B, then calculate the other indices. The multispectral band or bands, all the bands starting with B and the rest of their name doesn't matter. Remember that. Before further analysis, you need to go to the dataset web page and see if there is any scale factor. So as you can see here, there is a scale factor for all multispectral bands that should be applied before further analysis. That multiply to the suggested scale factor. So the multispectral band selected and processed. Now we need to calculate the NDWI first, because part of our study area covered by water and part of the rest of the area covered by soil, and I need to get rid of the soil to concentrate or focus on the water body. So it's very easy to do. Just NDWI sets to from multispectral bands dot normalized difference. You can calculate the NDWI based on spectral relation between band green, band number 3, and band near infrared, or band number 8, as you can see. So the output name will be NDWI. To my experience, the water body easily detectable by the NDWI. Pixels greater than 0.1 in the NDWI refers to the water body. And now I can make a mask layer by the NDWI and apply on the final index. Okay, now I have the NDWI and also I have the clear pixels and I have a water body mask. So in the next step, I need to calculate the colored dissolved organic matter. So if you search about Sentinel-2 water quality, you will find this page in the Sentinel Hub web page. So there are a couple of references here addressing Sentinel-2 most frequent water quality indices here. Color dissolved organic matter equation already addressed here, and here you can find its calculation or its experimental equation based on relationship between band number 3 green, and band number 4 red area. So how to calculate it in the Earth engine? That's our question. So the equation, the variable colored dissolved organic matter. So sets to from multispectral bands, make an expression. We want to do a calculation based on multispectral bands. So as you can see here, I can easily copy the whole of the equation into a quotation mark here and do some adjustments. For example, 537 is same. The multiply is same. Math dot exponential should be like this: exp and here minus 2.93 multiply to uh, division between band number 3 and band number 4. Put it into a parenthesis here, or curve bracket, or actually kind of bracket, and now the equation easily readable by the Python standard here. So the next step is defining the unknown variables. B or band number 3 here is an unknown. So define a quotation just like this, and from multispectral bands I'm selecting, or I'm actually referring B03 to band number 3 or green band. Do the same for the band number 4 multispectral bands dot select B4, just like this. The output name will be CDOM, color dissolved organic matter. The function at the end returning a result that is colored dissolved organic matter, but only for clear pixels. Dot update mask clear pixels. Now we are removing the cloudy pixels using this mask layer. Then we need to keep the values only for the water body, so another mask needed. Again, update mask, this time for the water body, just like this. And now we need to add some essential properties from input to the output by copy properties. From input image, the system time start property is essential and must be addressed in the output, because that's the essential parameter telling the date acquisition for every image or every data set through the time. Okay, now CDOM, color dissolved organic matter calculated, and for clear pixels, non-cloudy pixels, and only for the water body. Now we need to apply this function on Sentinel-2 images. Map here works like a kind of loop structure. So the function actually puts in the loop structure to do this calculation for all of 500 images available through the time. Let's run it again, and after a few moments you can see the calculated results. So again we have 593 elements here. Go to the feature, and this time only one element is available. That is colored dissolved organic matter only for the water body, with the system time start with millisecond format, explaining the date acquisition for every dataset. Okay, Now I'm gonna convert this image from image collection format into the X-array structure for the further analysis thanks to XEE library. So how to do this? Make a new code here, and now we need to install. If you follow already my tutorials, definitely you saw some updates in the XE library, how to call it into Google Earth Engine and Python API programming. So now I'm actually sharing the most recent update about calling and working with the XE libraries. If this method not working on your system, then you can follow the next tutorials on my channel, because the newer tutorials are updated with the newer actually strategies. So if you faced with any challenge, you can share your question, or you can check out the next tutorials that's most recently published on my channel. So now I need to install upgraded XEE library, and also we need to have the X-array library as XR. So the XEE library is installing. So maybe you face with such kind of warning. It's a warning that mentioned the XEE already built-in available, directly available in the EE, and you need to restart the session. But to my experience, you don't need to restart the session. You can move on and click on cancel. So now everything's fine, and here you can see a green check. So clear the output and import the X-array library. So now we can convert that image collection into X-array formats. So now I'm bringing datasets out from Earth Engine, and also bringing into the Colab and Python environment. I'm converting to a consistent format for the Python that easily uh, manageable by the Python libraries, because in the Python there are several functions and tools that we can apply on satellite data to get the state-of-art results. So again, xr.open datasets. Now I'm doing this conversion from X-array called the open datasets. The input is Sentinel-2, the engine is EE. I'm gonna call this dataset based on EE library. So the coordinate system for the input is EPSG4326 or WGS84. This coordinate system is same for all around the world. The scale or pixel size here is based on degree. 1 degree, 100 kilometer roughly. So, what I wanna call this dataset with 100 meter, 0.1 is 10 kilometer, 0.01 1 kilometer, 0.001 here is 100 meter. So, for the selected area or the ROI, let's run the cell, and after a few moments you can see the data sets. So now I'm converting an image collection into X-array format. So if you run the data sets, here you can see no longer image collection is available, and we have a multi-dimensional array structure. One dimension explaining the time, another one longitude, latitude, and instead of a band, we have a variable array of values along the time, latitude, and longitude. So this is a multi-dimensional structure, and this dataset from now on is on Python local analysis, and here you can see, even you can see the size of the dataset. So after conversion, we need to sort the dataset based on the temporal characteristic. So let's sort it based on sort by time dimension. We have a time dimension. So to my experience, multiply 1 allowing us to increase the speed of processing for this dataset. Scientifically, nothing's happened after multiplication because we are actually multiplying to 1. But actually, technically, it's a new dataset created apart from the previous one that is much faster for the analysis and make everything suitable and easy to manage for you in the Earth Engine platform. So now the data set, a new data set is sorted, then we can use it to calculate the monthly colored dissolved organic matter. Again, if you're faced with any challenge, feel free to put your comments below this video on my YouTube channel, and I'm highly suggesting and recommending to share this tutorial with other remote sensing fans in all around the world, because I'm gonna actually make the whole of process in the Earth Engine in the remote sensing using Earth Engine as easy as possible, because these tools are essentials for all environmental scientists and earth sciences. So, as you can see, the calculation process in the sorting is a little actually takes time, and it's a little bit longer than usual, but it's nothing because the volume of the analysis depends on the speed of the processing, highly depends on the volume of the data set, or the extent of area, or the period of time you want to select for the analysis. For example, here you can see after 1 minute the sorting process done, but from now on everything gets faster because I did a multiplication, a new data set created, and now we can do the analysis much faster than before. For example, I'm gonna convert the dataset into the monthly format. Monthly sets to get the dataset, resample the time dimension into the month format. For each month, get the median value over the time. So, as you can see, the new process is done just in 1 second against the previous 1 minute, because after this cell the whole of process getting faster because of simple multiplication. So now we have a monthly data set for 2024, 12 times data available. So let's do the visualization and see how the result looks like here. The colored dissolved organic matter, the variable name, dot plot, x-axis sets to the longitude dimension. We have longitude, latitude, and time dimension. Y-axis sets to the latitude dimension. Call time dimension. Call wrap. How many image do we have or should we have per row, because we want to have a multi-temporal plot. For example, 6, and call wrap is 6 image in each row. The next is the robust, increases the contrast of the output. So let's run the plot and see how the result looks like. So there you go. Here you can see the temporal dynamics of colored dissolved organic matter in the part of coastal areas in the Persian Gulf. You can change the color palette here by CMap. For example, I prefer the turbo color palette here. Now that's better. The higher organic matter actually highlighted by reddish pixels and bluish pixels showing lower organic matter in this area. So the next question, how to get export? We need to call the matplotlib first. Matplotlib.pyplot as plt, the essential libraries for plotting process and services in the Python environment. plt.savefig ensures to get export with the high quality, color dissolved organic matter with PNG format DPI 360 and BB box inches tight ensures everything, all the plot elements considered in the output and nothing gets over the layout frame. Let's run. In the left panel, after a few moments, you can have or you can see a new shortcut that shows color dissolved organic matter with high quality. Click on download and here you can see the results. You can save the result first and see the result quality that is very good for the reports and papers. There you go. You can use this tutorial for all around the world, and this is not limited to selected area. You can change the study area and see how the code working in different region. I hope you liked this tutorial as much as I did. Thank you for your attention.